Bonjour tout le monde. Merci beaucoup d'avoir bravé aujourd'hui pour venir ce séminaire. C'est un grand plaisir pour moi de vous introduire Dr. Brett Morris, qui est ici, en fait, qui était ici depuis hier pour donner des ateliers Astrophysics et GDAvis. Et aujourd'hui, il est ici pour nous parler de ça. Donc, après avoir obtenu un baccalauréat en physique dans l'astronomie de l'Université de Maryland, Brett a travaillé en tant que chercheur assistant de recherche à NASA Goddard Space Flight Center. Pour ensuite entamer des études graduées à l'Université de Washington. Donc, il est aujourd'hui titulaire d'un doctorat en astronomie et en astrobiologie de l'Université de Washington et ensuite travaillé en tant que postdoctorant, que chercheur postdoctorant à l'Université de Berne en Suisse. Aujourd'hui, il est ingénieur de logiciels au Space Telescope Science Institute à Baltimore, où il travaille, notamment sur des télescopes spatials comme Université et Roman. Donc, aujourd'hui, il est ici pour nous parler de la caractérisation des exoplanètes, entre autres des Jupiters chaudes, dont il est expert, et aussi de l'activité stellaire et comment est-ce qu'elle peut nous affecter nos données. Donc, c'est vrai.
Thank you, Lisa. That was the most beautiful version of an introduction of my CV that I've ever heard, because it sounds so much better when you don't know what any of it means. So thank you. It's more exciting when you don't know what's coming next because none of it makes sense. So thank you. I apologize that I'm speaking to you in English and the less beautiful of the languages. And I'm happy to be here. I hope that you are too, even though you're probably hostage in this building at the moment. And so I apologize that today is a weird day. I'm glad that you made it anyway. I hope that I can make you slightly forget for maybe 45 minutes what's going on outside, as long as we still have power in here. So we'll see how that goes. Today, I'm going to talk to you about phase curves of hot Jupiters. And we're going to talk about these strange worlds where the atmospheres are clear, which don't look like Montreal today. All right. So let's say you're driving late at night on a dark road. I imagine that happens here more often than it does in Baltimore. If you drive late at night on an unlit road, you might see a view that looks like this. You can't really see anything except the road. Does anyone know why the lines on the road are so bright? I promise this will be about planets eventually. How is it reflection?
Because you're projecting light on it.
That's true. How is it reflecting light back?
Well, there's something in the paint.
There's something in the paint. Do you know what's in the paint?
No, but I don't know. In Quebec, we ran out of it last year.
My condolences. I brought up a sore subject, didn't I?
It's on the roads in Quebec. Are they like getting first?
Yes. So they're actually glass beads.
Okay.
The way that you achieve this reflectivity of paint on roads is that you put glass beads in the paint. And the majority of the paint, which is underneath the glass beads, is white. And so that is reflective. But then in addition to that, you have these glass beads that reflect light backwards most of the time. You can think about this like, in the Apollo missions, they left these retroreflectors on the surface of the moon to reflect light back. This is the small, cheap version of that has not been to the moon. These are just glass beads. It turns out that if you shoot light directly at a glass bead and you're looking at a similar angle to where the light left from, it almost always reflects right back at you. And so if you leave these on top of the painted lines on the street outside of Quebec, then you wind up seeing really easily where the line was painted. Part of the reason why this is interesting to me was because I had to learn this the hard way. Does anyone here speak German? Good. Okay. So nobody's about to know what I'm about to say.
Bjorn.
Bjorn might. Hi, Bjorn. So when I moved to Bern, I moved to Switzerland in 2019. I moved into a beautiful neighborhood in this beautiful, quaint city in Switzerland. And I had heard this rumor about a crosswalk in the street where I crossed the street every day to walk my dog. The rumor was that the highly reflective paint that they put down on this road was exceptionally reflective. And the reason why it was exceptionally reflective is that they used Swarovski crystals as the glass beads in the paint on the road. True story, because Switzerland has a different budget than Quebec.
Anything.
What I would like you to think about is that you can tell what you're looking at by its reflectance properties. If you look at paint without glass beads, you can tell that it has no glass beads in it. It is less reflective. And there's this object that we've all been staring at collectively since the dawn of humanity called the moon, and it rotates around us. As it does so, it shows a face that is very illuminated, and at other times at different angles, you see a different illumination of the surface. There are still active astronomers and geologists trying to figure out the function to fit for the phase curve of the moon. The phase curve being how much brighter is the moon when it is fully illuminated than when it's at this angle. Because the function that determines how much brighter the moon is when fully illuminated versus just less illuminated is determined by the surface properties of the moon. Not just what material is it, but also what is its geometry. Are they fractal dust grains or are they a smooth surface? A mirror will reflect differently from my shirt. And that's partly to do not just with the fact that they're both, carbon-based, but also how the carbon is structured. And so using reflection alone, you can actually make some progress in determining what a surface is made of. And what I'm going to talk to you about today is how to apply this to planets. Here's a planet I love. It's the only planet with golden retrievers and pizza. And this planet has a moon orbiting it. This is a real picture. This is a single image. This has not been overlaid. This is a picture from L1 taken by a spacecraft looking at Earth. That is the moon. That is how dark the moon is compared to the Earth when they are both fully illuminated. The reason they are so different is because the Earth is water. You're just dust, you're leftovers. And the moon is basalt, mostly. And you can tell the difference, right? You can see it. And if you had a spectrum of these two, which is roughly what your eyes are doing at a very low resolution, you would also be able to tell that the basalt is fairly gray and the Earth is fairly blue. You would be able to do surface characterization and also atmospheric characterization if you did spectroscopy on these two surfaces, just from the reflection. And in fact, people have been doing this for a long time. There's this astronomer called Henry Norris Russell at Princeton 100 years ago, who set about taking photographic measurements of the brightnesses of all objects in the solar system known at the time that were bright enough to get these photographic measurements, where he essentially measured the mean magnitude, like apparent magnitude of the moon at a given phase, and then calculated its albedo. The albedo is essentially how much light gets reflected by the surface. If it's 0, it doesn't reflect any light. If it's 1, it reflects 100% of the light that hits the surface. And when he did this on solar system objects, he found that there was a categorical difference between the planets that have clouds and the planets that don't. Planets without clouds are generally dark. Planets with clouds are generally bright. So if you look at the albedo of a planet, you're, to first order, deciding whether or not it has clouds. He showed that the Earth's albedo, which is a little bit more difficult to measure in 1916, the airplane was 15 years old at this point, so they didn't have satellites yet. But what they did was they looked at the new moon and measured the brightness of the new moon, because Earth light reflecting off of the dark side of the moon would give you an estimate of the albedo of the Earth. And from that, they concluded that the Earth has an intermediate albedo. It is rocky and cloudy. Henry Norris Russell did the most work to come to that conclusion of anyone I know. And so welcome to Earth. We know a lot about it, but there are a lot of other exoplanets that we would like to apply this technique to, right? This is an exoplanet talk, so I inevitably had to use one of these plots. Here are known exoplanets as of this time last year. We've got solar system planets on top. And you can see that we're approaching Earth-sized planets at Earth-like orbital periods, but not quite there yet. We mostly have super Earths that are at shorter orbital periods, normal Jupiter-sized planets, often when they are interior to Jupiter's orbit, they are also inflated, and then the hot Jupiters, which can be very inflated. What I'm going to be focusing on today is largely those hot Jupiters, which fall in the box on this image. As you get to shorter orbital periods, you wind up getting hotter and hotter planets. Those hotter planets have different atmospheres because of the amount of irradiation they are subject to. And partly because of the fact that they are so irradiated and hot, they're very extended, which allows us to measure their properties by techniques like transmission spectroscopy. And so people have been doing great work on that topic for a long time. Transmission spectroscopy is the process of measuring the components of an atmosphere and the thermal structure of that atmosphere as light passes through the atmosphere. We also have thermal emission spectroscopy, which can be done at secondary eclipse, which will tell you something about the same information from a different geometry. It's going to be as light is emitted from deep within the atmosphere, how does it propagate through, and how do different species interact with that light? Like, is there carbon dioxide, and will that make opacity at a specific wavelength? But often left out of this conversation is the reflection component. If you were to look at that planet at its full phase, how much light would be reflected at each wavelength, and what does that tell you about what it's made of? And that's something we're going to talk about today. Often this is not a problem because reflected light can be quite a bit smaller than the thermal emission. And so most of the time, for the hottest hot Jupiters, there is so much thermal emission that the reflected light is just a small perturbation on top of it, and you can ignore it. A really prime example of this is this wild planet called Kelt 9b. It's 4,000 Kelvin. It's the temperature of a K star. And so its day side is emitting so much more thermal emission than any reflection it could possibly conjure that there's nothing to see in reflected light. So you're pretty safe making the assumption that it is thermal. I'm going to talk to you today about planets where it is ambiguous, where you have a mixture of reflected light and thermal emission. And in order to understand one, you need to understand both simultaneously. And that makes the problem a little bit harder. So the things that I want to talk to you about today, this is the outline of where we are going. We're going to talk about how thermal emission from exoplanets is emitted. We're going to talk about the shapes of thermal emission on maps of planets and how we can model that with as few parameters as possible. We're going to talk about how scattered light from exoplanets, how reflected light leaving an exoplanet atmosphere is generated, what the physics is there. We're going to talk quickly about how to make a framework for inferring whether or not a planet is cloudy using that information. And then we're going to try to identify which condensates, which cloud material is present in these exoplanet atmospheres. When I started this project, I was really interested in working on particular objects, right? It's really easy to get caught up in, we have a Hubble spectrum of this object and a James Webb spectrum of this object. And when you have those, that's amazing. You should study them, of course. But if you were able to use a mission that studied thousands of planets all at once to get out similar information, even if it's not as high fidelity and not as conclusive, that would be really valuable. And so I was thinking a lot about missions like Kepler, TESS, Plato, and in the future, Roman, Plato's the future too. And thinking about the contrast with missions like Hubble, Spitzer, and Webb, where it would be really great to use, for example, Kepler to figure out for a suite of planets, can we figure out if they're cloudy? And that's really hard to do. The rest of the talk is going to be me showing you that it can be done, but it is difficult. So we're going to get there by talking about Spitzer and Kepler phase curves, what they look like, what a phase curve tells you, what it encodes about the planet, how the observation is done. We're going to talk about how you synthesize reflected light phase curves and a model for doing that. We're going to talk about the framework that I constructed to measure the cloudiness of a few planets, and then talk about what the clouds are made of in Kepler 41b's atmosphere. That's where we're going. To get there, we're going to talk about a phase curve. What is a phase curve? I've said it a few times, but I haven't defined it. Here's a phase curve. This is throughout an entire orbit of a planet, what the relative flux of the system of the star and planet look like if you were to measure it with Kepler or Hubble or Webb. This particular spectrum, particular phase curve is generated from the phase curve that was observed for a particular hot Jupiter at Spitzer wavelengths. So this is actually realistic. This is a kind of real one. A transit is when the planet goes in front of the star, and you can see the transit easily. Less easily, you can see the eclipse. The eclipse is when the planet goes behind the star and you lose the planet's light. So we've got that geometry going on in those two places. Those are the signals that are easy to see. This has been done for actually quite a long time now. So going back to 2005, we had the first infrared secondary eclipses of planets where we could actually see planetary light go missing as the planet goes behind the star. And as we've gotten better at taking long duration observations with high photometric precision, we've also been able to see the curve that happens in between. The curve that's happening in between is generated by the planet reaching full phase. So as it goes from its less illuminated to more illuminated face in its orbit, you see the brightness of the system increase until the planet's light goes fully missing as it goes behind the star and then pops out the other side. This process has also been done quite a long time. In 2006, we have the first phase curve, although you can see it's pretty sparsely sampled, so people were a little skeptical. But since then, it's been followed up several times in different ways, and that is consistent with what the phase curve of this planet ought to be. You can see that the change in flux is quite small. We're talking about usually something like 100 parts per million or smaller, depending on the object, depends on how big and how hot that planet is. Then came Kepler. In 2009, the result that was presented in a seminar talk that I attended that made me want to do exoplanets was this plot. So I try to incorporate it in every talk I give. This is the actual light curve. This is a Kepler light curve with its real noise from the first 3 months of Kepler observations of hat P7b. You see the transit, and you see the eclipse, and you see the variability in between. This was with only the first few months of the multi-year Kepler mission, and so we have even better phase curves than this one for planets like hat P7. Turns out you can do the same thing in the solar system. It's a bit more difficult because if you're observing Venus from the Earth, you see it go through many phases. That's not so hard. But if you're looking at planets that are exterior to the Earth's orbit, you never see Jupiter at half phase unless you fly by, which we've done. So here's imaging from Cassini, which is a spacecraft that went to Saturn. As it went to Saturn, it took pictures of Jupiter until it flew by. So we have multiple phases, and then as it flew away, it took even more imaging. So we have a partial phase curve. We know how the brightness of Jupiter changes as you go around it. So shown in the bottom is as a function of angle between where 0 is looking straight at the bright side out to looking fully at the dark side, how the brightness declines. That's called the phase function. And we have these for Jupiter and Venus and several other planets too. And we can get spectra of the albedo. The planet is more reflective at certain wavelengths than at others, and that has to do with what materials are in the atmosphere. And so you can measure the spectral features that correspond to different reflectances from species like methane and ammonia in Jupiter's atmosphere, looking at this curve. So we live in a good time for comparing these quantities between the solar system objects and the distant exoplanet systems. And when we look at those distant exoplanet systems, unlike Jupiter, which is rather cool, we see light curves that come out like this. The reflected light component is often small or similar in amplitude to the thermal emission component. You can see that these two are different. The reflected light goes to 0 when the planet is between you and the star. Otherwise, it's a bad situation. I don't want that. If you have thermal emission, the night side is not usually 0 Kelvin. And so even the night side of the planet is emitting some flux back at you. That determines the offset here between the thermal emission and what would be no flux from the planet. And so together, you can measure the day side temperature and the night side temperature from the vertical offset between the thermal emission and the bottom of the phase curve during the secondary eclipse. But how do you know the reflected light component? That depends on that variable called the geometric albedo, how much light gets reflected, which we would like to measure. So how do you measure these two together? There are a lot of ways that you can parameterize the thermal emission and or the reflected light. So let's go through some of the ways that people have addressed this in the past. One straightforward way to approximate this kind of phase curve shape is a series of sinusoids. And Fourier taught us that if you do that enough, you can fit anything. And so what most people do is they first fit a single sinusoid to the phase curve. And if that doesn't work, if there's still leftover signals, they add a second sinusoid at twice the period, or twice the frequency, and then continue doing so until it fits the majority of the phase curve, right? That's one approach that often works for very hot planets with little reflected light. Another approach, which can be a bit more challenging to write as software, would be a model where you have a bright region on a planet and then a dark region on a planet. So the planet is not uniform everywhere. You're observing a brighter region and a darker region as it rotates around the star, and they both contribute to what you see as it goes around. That kind of model was employed to explain this phase curve. This is the phase curve of 55 Cancri E observed with Spitzer in the infrared. At these wavelengths, we're really looking at thermal emission, and you can see that the hottest face of the planet appears just before the secondary eclipse. If the planet had a surface that was perfectly uniform, you would expect the hottest face of a tidally locked planet, especially, to be facing you directly at secondary eclipse. So you would expect that peak to be right where the secondary eclipse is, and it's offset, which tells you something about what's going on the surface or in an atmosphere. We don't know if it has an atmosphere. So to model this, they created two models which have different surface temperatures in different longitude regions, and then stuck those into a model that rotates the planet and produces a phase curve to infer the temperature of the planet and how wide that hot region is on the planet. Okay, so we're getting more complicated. Now let me make this so complicated you don't even want to learn it. So in 2014, my collaborator on this project, Kevin Heng, wrote a paper where he tried to derive a series of equations that describe temperature maps and wind maps on exoplanet atmospheres. The goal was to parameterize them using spherical harmonics. To incorporate lots of physics, he kind of went through a list and said, what are all of the physical processes that affect the winds and the temperatures of exoplanets? They include things like drag and magnetic fields and rotation and insolation. You've got the star on one side. You've got all of this going on in an atmosphere that is rotating. And so in this paper, there are 300 equations that derive a set of wave functions on a sphere to describe a temperature map and a velocity map on any planet. And I said, that's great. How do we do less math? And what we found was that the product of that paper is that you can produce generic temperature maps for a planet depending on parameters that have to do with the gas physics in that atmosphere. You can perturb the spherical harmonic shapes in the same way that an irradiated atmosphere that is rotating will be perturbed. So if you've ever looked at a temperature map of a GCM, of a simulated exoplanet's atmosphere, you often see that there's a hot spot and it's offset from the most irradiated point on the surface, and that there are these patterns of heat that extend around the equator and a super rotating jet around the middle. And all of those features are usually pretty small scale things that you wouldn't see in a phase curve, but there's some global trends that you could approximate in a phase curve. One of the things that I worked on to make this project work is that in 2021, we wrote a paper showing that you can use the spherical harmonic basis functions that Kevin derived in that paper to succinctly describe temperature maps of planets with very few free parameters, because the map of the planet that comes out of that framework is already pretty accurate. So you don't need very many free parameters to describe the map of your planet. Here are outputs from GCMs. Those are some of the features that I was just describing. The center of the map here would be the substellar point. That would be the most irradiated point on the planet. The opposite sides of the plot represent the back night side of the planet. And in between, the middle of the plot would be the equator and going to the pole in either direction. You can see here that as you get more irradiated planets, they get hotter, but that also depends on the structure of the atmosphere. And what we showed in our paper in 2021 is that with very few free parameters, using only the first spherical harmonic mode in this basis set, if you squint your eyes, those are almost the same. We quantify what that means. We say, how close are they to one another? And if you were to measure this with a phase curve, would they produce statistically detectable differences? And the answer is not really. You can go up to arbitrarily high spherical harmonic order and reproduce smaller and smaller scale features on the surface, but you don't generally need to. Here are some fits to Spitzer phase curves. These are real observations in the infrared of hot Jupiters. And as you integrate the spherical harmonic map of the temperature map of the planet based on the observability of each section of the planet's atmosphere as it rotates, you can explain pretty much every Spitzer phase curve that's out there without too much difficulty. Each of them gets two fitting parameters for the phase curve, and everything else pretty much takes care of itself. So we were pleased with that result. We thought, even though this is an approximation and there are some assumptions in there, we can make maps of exoplanet temperatures. This is the temperature forecast on several planets. We liked that. We thought that was fun. We also thought that it was neat that you can compare different band passes. So here, each column represents one planet. Each row represents a different Spitzer filter. And you can see that in some filters, planets appear hotter than others. And that has to do with the depth into the atmosphere that you're looking at that wavelength. So there's some neat physics in there. The planet that is wildest is the one that I mentioned earlier. It is Kelvin 9. You see that its day-side temperature exceeds 5,000 Kelvin in some places. It's a G star, depending on where you look. And we found that we could use phase curves from the Keops Space Telescope to measure the same thing. Kelvin 9 is kind of a strange planet for lots of reasons, but one is that since it's 5,000 Kelvin, the peak of its SED is in the optical. So when you measure an optical phase curve, you're looking at the thermal emission. And so we could measure the day side and the night side temperature of this planet, which is just absurd, with great precision using the optical photometry from the Keops Space Telescope. If you haven't heard of this, it's a really small telescope. It's about twice the size of this lectern. It's a 30-centimeter mirror, and it only does photometry of a single star at a time. So we said, let's point it for 4 straight days at this one star. And we collected beautiful phase curves, which allowed us to measure temperature maps. And those temperature maps are partly assumed in that we don't have latitudinal information coming from the phase curve, but we do have longitudinal. And what you see on the right-hand column here in this work by the graduate student Catherine Jones in Bern is that you can predict the dissociation of hydrogen across the surface of the planet based on that temperature map. On the day side, it is hot enough to disassociate H. On the night side, it should recombine. Weird. It's a cool planet. Okay, so we might have the thermal part down. We've got a way to solve that problem. What about reflected light? Fortunately, Kevin also solved that problem for me. Kevin wrote a paper in 2021 where he showed that there is a way to recast the algebra so that you can solve for the phase curve of planets with few assumptions. And I'll explain what I mean by assumptions. If you think back to your first lesson on optics, one of the things that you learn about scattering is that there is this thing called a scattering phase function, which determines if an object is forward scattering or back scattering. And as you look at it from different angles, how much the scattering changes. And often people compute reflected light phase curves by using a Monte Carlo approach where they actually shoot photons at the planet and see how many come back. Or they assume a given phase function for the material that's doing the reflecting, and then work the algebra so that you can produce a phase curve from that phase function. What Kevin did in the paper that I'm discussing here is that he came up with a way to put any phase function into his framework and get a phase curve out analytically without doing a Monte Carlo approach, without doing the difficult part that is often very computationally expensive. And so in this work, I'm going to be using a Cornet-Shanks scattering phase function, which looks a bit like a Rayleigh scattering phase function, except that it can be a little bit more strongly forward or back scattering. There's one extra free parameter that determines if it's slightly dominated by one side or the other. Our first proof of concept that we could use this was on a planet called Kepler 7b. Kepler 7 is famous for being the most asymmetric phase curve yet measured, depending on signal to noise cuts. This is by far the most confidently detected asymmetric phase curve. And it's really interesting for a bunch of reasons. One is that it's a warm Jupiter rather than an ultra hot Jupiter. And so you can see here in the posterior inference, the thermal emission component is actually quite small. We're accounting for it, but it is small. The reflected light accounts for most of what you see, and the reflected light is asymmetric and has bumps and wiggles in it. It turns out that you can produce a model that explains this really succinctly using Kevin's framework. The way that it works is something like this. The asymmetry arises because we don't think the planet is symmetric. It would be strange to think that it was, right? The reason we don't think warm and hot Jupiters are symmetric is because the substellar region is very highly irradiated. And the material that makes up clouds, which are often very reflective, can disassociate, can break up, can become unstable if it's highly irradiated and at a high temperature. So you might wind up with a region of the planet that is darker than the surrounding region, which is cloudy. Clouds dissipate in the substellar region, and they are stable outside of that region. But nobody has a perfectly predictive model for how clouds work. Sorry, theorists. So we don't know how offset this region should be from the substellar point. We don't know how wide it should be. It's going to depend on wavelength and the temperature of your planet. It's going to depend on a lot of things. So one of the things we're doing in this work is we're trying to get a first answer to these questions. What we did is we fit this particular phase curve using that model with a darker substellar region of unknown width and two different albedos inside the dark region and outside the dark region have two different albedos, and fit for all those parameters simultaneously in a Bayesian inference framework. Because this technique that Kevin came up with is really just sines and cosines in the end. So it's extremely efficient to add to an MCMC. So we could do this in finite time on my laptop, and that's what we did. And so then after we did Kepler 7, I came back to thinking about the planet that inspired me to think about planets, HAP-P7 again, where we have this near equitable contribution between the reflected light and the thermal emission component in blue and orange on this plot. There are two other curves in green and dark red, which represent stellar artifacts that arise in a phase curve. One is Doppler beaming, the other is ellipsoidal variations. So what I wanted to do was say, okay, that plot that I love, that had a few months worth of Kepler data. If we take all 4 years of Kepler data, all 60,000 fluxes on this star, could we model them all simultaneously with the thermal emission model, the reflected light model, the stellar artifacts? Can we not bin those models? Because if you're binning, you might cancel out instrumental systematics that are occurring in time. So let's compute this model in real time at every photometric point because our model is cheap. And let's also put a Gaussian process in there to account for the stellar systematics that we know are there. That took me a long time to code, but I did it. And so I'm going to show you the results of doing that. So for Kepler, for HAP-P7b, we have these rotational systematics that come from the star rotating in the background. So we have a Gaussian process in the time domain that is removing the stellar rotation. We put all of this into a Bayesian inference framework to retrieve the physical parameters that describe the scattering and thermal emission properties of the planet. And then we run it on all the Kepler data for 5 planets that we chose to span a range of temperatures in the region where clouds should be stable up through where clouds should dissipate. Thinking It would be a really neat proof of concept if we could show that the really hot planets don't have clouds. It's a little more difficult than that. I promised you that this would be Bayesian inference, so here's your corner plot. We are inferring parameters like the geometric albedo, so this is how much light gets reflected by the entire planet. For this particular one, KOI 13b, it's likely actually a brown dwarf orbiting a star, and so this is kind of an oddball among the planets that I'm showing you. It has a high albedo, this one's 0.3. C11 is a thermal contrast parameter. If it's 0, the day side and night side are the same temperature. If it's larger, the difference between day and night is larger. Scattering asymmetry parameter G is it forward scattering or backward scattering? If it's 0, it is neither. It's more closer to isotropic. And omega 0 is the single scattering albedo that is in a single scattering event on the surface, wherever the reflection is occurring, how much light comes back to you. Here you can see it's almost 90%. That is a lot of flux coming back at you on this surface. I also showed you that we anticipate these planets are not homogeneous. And so we coded up a way of having these inhomogeneous planets where there's a darker region. There are two albedos. There's in the dark region, out of the dark region. There are two longitudes that define where the dark region occurs. And then we infer for each planet a model that is homogeneous and a model that is inhomogeneous. And we do model comparison to decide which one is more likely a better fit. Of course, all of this requires statistical inference techniques and not doing it by eye, because this haze you see in the background that looks a bit like Montreal's sky today is the data points. There are 60,000 of them, and we're looking for something that's really close to the noise level in individual measurements. If I were to bin the entire light curve, you would be able to see that this is a fairly good fit for both plots. But the binning can be sort of betraying because there is high frequency and low frequency variability happening on the star all the time. And so binning over that will start to cancel out some real effects, and we don't want to do that. So I'm intentionally not showing you here. In order to do the comparison between the homogeneous and inhomogeneous models, I use something called leave one out cross-validation, which is a technique that statisticians have been using with great success in recent years to figure out if one model explains your data better than the other. It requires a lot of linear algebra, and so it's a bit intimidating to take on your first time, but when you do, it gives you some really useful statistics. One of them is that you can compute which model is preferred by your data and how strongly it is preferred. This parameter is called the weight. And what I'm showing you in this plot are points colored by their weight, where here, each point represents a different planet. The vertical axis is the albedo that we infer, the horizontal is the temperature. The label for each planet is up above. The color of each point tells you if we believe strongly that it is homogeneous or inhomogeneous. That would be red or blue. And if it's somewhere in the middle, if it's not a very dark color, you shouldn't really believe anything. The darker it is, the more you should believe it. Of course, that's all subject to the idea that you've given it two possibly plausible models to begin with. So it could be that these planets are not well described by the model that I use, but one is more preferred than the other anyway. So this is not to say it is homogeneous or it is not homogeneous. It's of these two, which is the better fit, right? There could be third models that are even better fits. What you see is that KOI 13b looks inhomogeneous. The preference is strongly inhomogeneous. Trace 2b, which has almost zero geometric albedo, it looks more homogeneous than inhomogeneous, but the preference isn't very strong. That's what you would hope to see because there's almost no signal from reflected light if the albedo is 0. So you don't want to see a strong preference either way. Everything that happens in between, we don't really know. The one point of truth that we wanted to check is that Kepler 7b is confidently inhomogeneous, because I told you earlier, we're pretty sure that's the most asymmetric phase curve. And indeed it is. So once we've identified planets that are likely inhomogeneous, and we've done this fit, and we now have posterior inference for the albedo of the reflective region, we can say, does that albedo match a given species? What are those clouds made of in the more reflective region? And fortunately, folks who think a lot more about chemistry than me have done a lot of work on this topic. Here are stability curves, which tell you the species that are likely to form, likely to condense within an atmosphere at a given temperature and pressure. If you fall below or to the left of a given curve, then that species is stable. And if you fall above or to the right of the curve, that species is not stable. And so up at 2400 Kelvin, for example, no matter what pressure you're at, none of these species are stable. But down at 1200, they all are. And in the intermediate range, it depends on the pressure that you're looking at, which will depend on the wavelength that you're using to observe that atmosphere. And so we can start to compare, because our thermal emission model gives us a temperature of the planet. Radiative transfer folks can tell us what depth of the atmosphere we're looking at. So we have like a temperature and a pressure. We have a geometric albedo. We're starting to get to a place where we could say this species may be plausibly the cloud in the atmosphere. How do we actually do it? Well, here's an example. This is Kepler 41b. This is the full corner plot with all of those parameters. So we've got a geometric albedo, day-night contrast, scattering asymmetry. We've got the albedo in the dark region, the albedo in the bright region, and the two places where the darker region is defined by. We can also look at how reflective it is in the dark region and in the light region. In the light region, Kepler 41b is very reflective. It goes to the top end of the range. Now, folks who think about optics can use scattering to tell us what the single scattering albedo and the scattering asymmetry parameter ought to be for a single species. You do this in a computer using theory. It's been around a long time. It's taken measurements of refractive indices that are more modern to get precise curves like this, and great computers to do it efficiently, but you can compute. I've been telling you about this single scattering albedo that is part of the phase curve model. You can guess if my planet were purely iron, which it's not, then this is what its single scattering albedo would be if the particle radius was this many microns. So we can also draw in the particle size. We can say if we have a cloud of iron where they are all 1/10 of a micron, we would expect a single scattering albedo of 0.2. And we would expect the scattering asymmetry to actually be slightly negative, which means slightly backscattering. And then we can go and check for the phase curve that we measured, how the omega and the G compare. So we can start to rule in and out different species based on theory. So this plot is horrendous, and I hope you'll join me in trying to understand it. These are the posterior distributions for the single scattering albedo that we infer from the phase curve in reflected light of several planets. These are those same curves that I showed you. I flipped the axes. So you can say Kepler 13b, KOI 13b, has a single scattering albedo of 0.8. 0.8 can be consistent with these species at this radius, or these species at these radii. And then you can also come over here. You can say, okay, well, KOI 13 seems to have a single scattering, a scattering asymmetry parameter that does not agree with any of these species. So maybe we should cast doubt on that fit. So let's look at another one. Kepler 41b is the one that I've been using as a motivating example. It seems to be mostly constrained to this part of the plot. So within a sigma or a few sigma, it's probably one of these three species. Now, what is the G for that planet? Well, it's somewhere over here. That is constrained to a fixed range of particle sizes for any of the species. So we can start to say that, KOI 13b, not sure if it has clouds. If it does, we're probably not fitting them well enough with this model. But Kepler 41b, this model could be enough. Now, let's go one step crazier if you're willing to indulge me. We have a temperature map. We know the longitude where the atmosphere gets less reflective. If we read off the temperature map, what the temperature should be at the longitude where the reflectivity changes, you're measuring the temperature where the cloud is no longer stable, which is another property that we know for these materials. We know that corundum is not stable at certain temperatures. So you can overlay this two pieces of information together. You can say, given the longitudes where we expect the dark region to be bounded by, And given the property of the material called forsterite, which is a particular condensate that we expect to be clouds in many of these atmospheres, you find that if you put forsterite within the depths of the atmosphere that correspond to these numbers in bar, you would get, this is where it gets trippy, you would get dark regions that correspond to what we measure. So the gray posterior in the background is the posterior inference for where the dark region is going to be. The line with colored points going through it is what models say forsterite should do if it is at different depths within this planet's atmosphere, where it is stable. And so we can start to compare and say, at what depth should the cloud deck be? And it's somewhere in the hundredths of a bar. Oddly enough, theorists who know a lot more about clouds than me have been predicting that this particular species, forsterite, is a likely condensate in many of these hot Jupiter atmospheres, and it takes up a lot of the real estate in the temperature regime that we're talking about. So if we put it all together, we're getting closer to identifying the clouds in planets in other atmospheres. We're not quite there. I'm not going to say that forsterite is the only option for Kepler 41b, of course, but we're trying to do, by design, almost an impossible task to prove that we can make progress on it, which is that when we think about phase curve photometry, not spectroscopy, when we think about the photometry, people often say you won't be able to identify what species is in there because it's just photometry. And what I would like to provoke you into thinking about is that even photometry can be revealing if you know something about the wavelengths that you're looking at and you know the physics that's going on the surface. Can you imagine how much better these fits would get if you had multi-wavelength information? They would get way more expensive, of course. There's an extra dimension to worry about. But those data are coming, of course. We have high signal to noise, spectroscopic phase curves from James Webb that are starting to come in now. And if you want to fit those correctly for their variable albedo as a function of wavelength and longitude, then you're going to need frameworks like these. And so if that's something that you're starting to think about, and I know some of you are, then feel free to reach out. All of the code that produces all of the plots that you've seen is open source and currently on GitHub and documented so that you can go read how it works and make it work for you. One of the things that I haven't talked about, but I'd love to talk about until you are sick, is that I coded this all up in JAX, which is a language that is auto-differentiable and gets compiled. So it looks like Python, but it runs at compiled speeds on the CPU or the GPU. And so whatever computer you have access to, you would be able to run this code pretty efficiently. So I hope I've convinced you that we've got a thermal model, a reflected model. We can apply them to planets, even just in photometry without spectroscopy, and start to talk about what the clouds are made of. Thank you for joining me on that journey. That was a long one. What do we think? Tear me to pieces. Let's do it.
So, yeah, this is amazing. So, I mean, of course, the Kepler is good, but web is also amazing. So I can just imagine that you would be able to perhaps even expand your framework to other physical parameters, make it more complex, because there will be, better quality data and more information that we're going to cover.
Absolutely. So, yeah. So going forward, right? Here's what we've got. Here's what's coming. We've got Hubble, Spitzer, Kepler. Hubble's still going, but the others are dead. That's still going. Webb is here and it's producing stuff. Plato's coming soon. W first is Roman now, and Roman's going to be great if it's not there. Chaos is currently going. That's great. Gaia, it doesn't really matter for us. James Webb sits at a different wavelength regime than Kepler, and that affects the physics that you can infer. This is near spec bandpass from 1 to 5 microns. Goes a little bit blue up there, but the throughput is pretty low. If you assume that a planet has a constant albedo with wavelengths, just to say a gray planet, and you take the equilibrium temperature of that planet, calculated naively, and you take the black body spectrum of the star, scaled to that albedo to give you the amount of reflected light you would get from that planet, as a fraction of the reflected light plus the thermal emission from that planet, given its equilibrium temperature, you would measure a reflected light ratio with the total thermal plus reflected flux of this curve. So up in the UV, you would be getting 100% reflected light. There's no thermal emission from a planet in the UV, I hope. That would be a strange planet. If you discover a planetary chromosphere, let me know. And then as we get out towards the thermal infrared, it is mostly thermal emission. The reflected light drops to a small fraction. But near spec is covering a range where planets that we know and love, like HT 733, go from mostly reflected to mostly thermal emission. And so part of the reason why I bothered doing this wildly difficult exercise is that we're going to be dealing with planets that have the mix. It's not going to be, this is just reflected, it's not just thermal. And frameworks that incorporate that uncertainty, especially in the way that it correlates with wavelength, because we expect that to be nearly a smooth function, that requires a lot of thought and coding upfront. And so I wanted to get a head start on that. And we're starting to see that now, right? We've got planets where you can really see that there is more reflected light at the bluer wavelengths, which is what we expect and physics tells us must happen. But how you incorporate the effect of the increasing thermal emission as you go to longer wavelengths is something we haven't truly had to deal with because it's mostly been photometry or narrower band spectroscopy. So this is something that I think is going to be more and more of a problem for all of us in the near future.
For this amazing topic.
Thank you.
I don't know if anyone else has any questions. Otherwise, I might ask many of them. So I think it's fantastic they can start characterizing clouds with reflected light or optical phase curves. So you showed the Kelp-9, like, I don't know if it was a joint fit or if it was just like individual fits to phase curve at different wavelengths. If it is not a joint fit, have you started doing joint fits where you can infer cloud properties from two different phase curve in the infrared and optical, and also start ruling out species or temperature, pressure, deck of the cloud?
Great question. So this plot is the day side, night side temperatures in 3 band passes for one planet. The planets, the missions go roughly in order of wavelength. So CAPS probes the upper part of the atmosphere, which is hotter at this, other way around. This always confuses me because it also depends on wavelength in ways that are not intuitive. But Spitzer is probing a different layer of the atmosphere than TESS, which probes different than CAPS. So you get different temperatures in each one. These models are simultaneously fit. Here, we went through the trouble of fitting all of the data simultaneously, which was really a Herculean effort put together by Catherine Jones. And Kelp-9b is the planet for which we expect absolutely no clouds under any circumstances. This is the one where the night side is 3,500 Kelvin. So we don't expect any clouds there at all. And so there were no clouds to model in this exercise, which is why we were able to get really beautiful fits with only a thermal emission model. Also, if you compare this to a star, which might actually be an apt comparison, right? Kelp-9b with a 5,000 Kelvin day side, more like a G star than us. Stars have small albedos. We know this from polarization phase curves of eclipsing binaries. The amount of reflected light that leaves a star that's being orbited by another star is actually a few percent. It's quite low. So we expect objects, whatever you want to call Kelp-9b, we expect objects like Kelp-9b to be not very reflective. And using a thermal only model, we were able to get a great fit consistent with the noise. So it is possible that there's a reflected light component there. I don't think we're seeing it. I think you're more likely to see it in the UV, but that would be difficult. Yeah.
How about at P7? So you showed a fit where you could Kepler data. what I've read in the literature in the past is that people have found, or people have analyzed Kepler light curve of the same planet and then found basically like a moving hotspot from one orbit to another. And what you're showing, we basically phase with them.
You took all of the bait. These are all the things that I prepared for. Thank you, everyone. Okay, so there's a paper by Armstrong et al., 2016, which claims that the phase curve of HAP7b is varying. And I have always wondered if that was ever possible for several reasons. One is that if you look at Jupiter, it usually looks like Jupiter. Time of year doesn't really matter. Time of its year doesn't really matter. Usually looks like Jupiter. How could it be that a phase curve would totally change from being bright before the eclipse to after the eclipse over a few orbits? That seems a little wild. And so I went about testing this. I did the fits that I did in this exercise multiple times on different bins of data. So here I'm showing you yearly fits, breaking up the Kepler data into 4 years to measure the albedo, the reflected light albedo, not some phase curve model that may or may not be physical. This is a physical model for the albedo. It's consistent with a flat line as far as I'm concerned. I don't think it's varying. If it were varying, we would be able to test that. And I don't think we see that information here. HAP7b is the red one, the red points, consistent with a line. So as far as I'm concerned, I don't think that's happening on this planet. I think that's likely to happen if you don't incorporate the stellar variability that's happening underneath the planet's variability as well. And so there's a really great paper by Lally and Vanderberg that came out a year ago now, that shows that granulation on the star can fully account for the variability that was observed in the Armstrong paper. So you have to account for the star in your phase curve fit, which is why we included a GP in these fits. If you don't, you get variable planets. That's a little problematic.
I love that you're focusing on photometry rather than spectroscopy, because I feel like the field is usually turning towards spectroscopy in order to confirm or distinguish between scenarios. Do you think this is like a new avenue for doing the same science that we've been doing for these like large gas giants, but doing that for smaller planets for which you might not have enough signal to have spectroscopic information, but you could start to do the same science with smaller planets, figuring out whether they're clouds, which cloud species they have?
I think you could try. I think there are challenges that will make it hard. The first challenge is that for a gas giant, we assume they have atmospheres. For a rocky planet, we can't make the same assumption. And so whether or not it has clouds depends on having an atmosphere to be cloudy. And we don't know a priori if 55 Cancri E has one or not. So how would you incorporate models that have and don't have atmospheres? And then among the atmosphere models, ones with and without clouds, obviously a hierarchical model like that is ultimately where we want to go, but that's expensive and that takes a lot of work. So I think right now, this will be a specialty application that you can use to procure more information from existing data sets. I think ultimately where it needs to go is in the direction of handling both. If you took time series photometry of TRAPPIST-1b, because maybe TRAPPIST-1b, the signal to noise is low enough in its phase curve that you would want to co-add many orbits and use the white light phase curve from Webb. If you did that, then maybe you would be able to say it is reflecting as though it is a cloud-free, atmosphere-free basaltic surface, right? You could try to make that analysis, but until someone then did the transmission spectroscopy to prove that it has no atmosphere, I wouldn't believe either very much by themselves. I think the answer is always yes and, more than I can do it better than you, because I don't believe that's true. I think we all need to do it together and prove each other right. I think that's what we need to do.